final speaker this morning is Sam Taira from UCLA.
It's on? I don't see the light. Okay. Is there a plug? Thanks. Can you hear me? Yeah.
Resolvent-inspired flow control of turbulent flows.
So I need to share, right? Yep. Serious. Yeah, they cut it. This one, right? It's okay. It's okay. It's okay. I'll just use this. It's okay. Okay, thank you. Okay, so I stand between you and lunch. Hopefully it won't take too long. I noticed that this crowd has very strict standards for grammar. So initially my title had flow control here, but I removed flow so it's not repetitive. So hopefully I have your approval. But I am very honored today to give a talk in front of this crowd. I come from the flow control community, and I'd like to get your feedback on what you think about our work is. Okay, so acknowledgements. This work was completed with a lot of help from our former students. So there's Chian Ye, Chung Liu, Yang Sun, who they graduated already. You're going to see some contributions from John and Callum. We also have wonderful collaborators that help us quite a bit: Peter, Daniel, Stuart, and Yoimi. Okay. So our approach is to see if we can use resolvent analysis as a powerful tool to give us insights into how to control flows. Okay, so I'm going to talk a lot about it. Initially, I thought about putting a talk together that talks about two different applications, but of course, that's way too much. So I'm going to focus on airfoil separation control. If you're interested, I can talk about open cavity flows, but I'll save that for a different time. Okay. So the objective of our work is to design an efficient and effective physics-based flow control technique. And I'm going to say physics-based, and then there's a meaning for that. And what we're going to try to control is a nonlinear, multi-scale, high-dimensional turbulent flow, which actually is not an easy thing to do, as we have seen from a lot of the previous talks. And our goal is not just to suppress some instability. We're actually going to try to change the mean flow. Okay. And we want to provide guidance for performing flow control, like I said. And this is something I'm going to come back to, all right? So I say, e.g., location, frequency, et cetera, but I'm going to go through this and try to convince you that we now have a really powerful tool that can really guide flow control folks and see if we can change the flow. And one thing we want to do, although I'm going to do this anyways, is I want to avoid expensive parametric investigations. Right? So we want to go away from trial and error. And what I mean by that is, let's say this is the baseline flow field that we have for flow over an airfoil that's separated. This is what we did, but this is precisely what we want to avoid, right? Simulating each and every kind of different control setups and how the flow is going to respond. Each of these are from an LES calculation. Of course, they're expensive, right? So we want to avoid having to go through hundreds and hundreds, or maybe even thousands of them, either in an experimental setup or in a simulation setup. Okay. All right. So what we're going to resort to is modal analysis, as all of you are quite aware of. And this is kind of a standard style I use, but there's a flow, and if you can see the structures, we're hoping that the mathematics can tell us how to extract these structures, right? And I love this example that, our colleague William Wolf published recently, in that this is flow over a landing gear well. And even for something as complex as this, you can actually pull out some really nice POD modes, right? So this gives us a lot of hope that we can extract these coherent structures that might be useful for something that we want to do, in our case, flow control. Okay, so thanks to our colleagues who've spoken about this, I'm going to be able to go through this really fast, but what we're going to rely on is this global analysis technique. So you've heard of resolvent, but what we're going to do here is we're going to decompose the flow into some base flow and some fluctuation. In our case, we're going to use the mean flow. So we're going to linearize about the mean flow, and we're going to stick all of our nonlinearities into this F prime over here. And we're going to express all that in terms of some spatial mode and e to the I omega t. And if you go into the Fourier space, if you don't have F, we have the standard global stability analysis, assuming that we have an equilibrium state for our base. But if we have like a time average flow, then maybe we can't get rid of F. We'll have the resolvent analysis, right? So here in our case, we're going to stick to this airfoil separation control. So we're going to have baseline flow that we're going to get from the large eddy simulation. We're going to be using that. Okay. All right. Now, this input and output relationship that we have been talking about. So we have F and you have some operator, which is the resolvent, and you'll have Q hat, right? And just so you know, our flow is actually an unstable flow, okay? So we're gonna have to do some, we're gonna have to be a little careful about that. What we're gonna do is we're gonna do something called the temporal discounting. This is something that we came across from Mihailo's work, which is quite nice. There, of course, is a different way to do it. For example, Tim's group is using the eddy viscosity approach to take care of this matter. Now, if you look at this resolvent, which is this operator, is just a cartoon, you can perform an SVD of this, and you'll have the right singular vectors and left singular vectors, and you have the gains right in between. So if you were to multiply F, your input, to this matrix right here, and if anything aligns in the direction of these singular vectors, and if the inner product is something sizable, of course, you're going to multiply by the gain, right? And then you're going to see an output in terms of Q. Visually speaking, in terms of fluid flows, what we're going to see is we're going to have some modes that are going to come out as the, let's say this is a primary mode. You're going to have the forcing mode right here. It's going to be for the particular frequency that we have. It's going to be amplified by a certain amount, and then you're going to see the response that way. Now you could say, well, Sam, that's ridiculous. We can't force right here. You're absolutely right, and we're going to come back to this, right? But for now, don't worry too much about it. Okay, so let's talk about this actual example that we were that I've been talking about. Okay, so here I'm going to consider a NACA 0012 airfoil at a modest angle attack, 9 degrees, and a modest Reynolds number of 23,000, core-based. Okay, and it's periodic in the span-wise direction. It's slightly compressible, 0.3, and this is a well-resolved LES calculation that we're going to consider. And what we're going to do is to see if we can come up with a way to change the behavior of the flow, the mean flow that is, okay, so for lift enhancement or drag reduction. Now, we were requested by our sponsor to consider this actuator called the heat flux actuator. Actually, this is called the thermoacoustic actuator. It's usually made out of really thin things like graphene that you can see through. But this funny material, you can add or you can put electrodes on it, pass AC current, and it heats up and emits enormous amount of sound. So we were told, like, maybe can we consider this to put it on the leading edge and see if we can do anything in terms of modifying the flow. So we said, okay, we can certainly do that. The way we modeled it was by having a sinusoidal heat flux coming in over time. What we wanted to do is, well, what frequency should we be actuating? And in what spacing in the span-wise direction should we be considering, right? These two things were unknown to us, okay? Now for the location, for the moment, bear with me, but I'm going to put this actuator right here at the leading edge, okay? You could say, well, Sam, how do you know? Well, we've been in the flow control community for some time. We know that's a sensitive spot, but we'll come back to this. I'll justify that later, okay? I also am choosing a particular actuator type, but we can also come back and see if that is indeed the optimal type of actuation, okay? The only thing that I cannot determine at the moment is how much I should be actuating at, the amplitude itself. Tim, you had a question? Oh, I thought you raised your hand. No. Okay. Right. When my advisor raises my hand, I just kind of freak out. Sorry. All right. So all these things. All right. Now, here's the baseline flow, right, at the top. And here's the controlled flow, right? And this is a movie of the turbulent flow field. If it plays, oh, here it is. Okay, this is what happens. They all start from the initial condition, same initial condition. This is with a 2D strip of actuation at a particular frequency. It's really interesting. If you do it at the right frequency, it chops up these rollers. These are Q criterion isocontours colored by, I believe, streamwise velocity. It actually turns the flow into 2D flow, it relaminarizes. Okay. If you put in some 3D perturbation at the leading edge, it breaks up these vortices early, and it doesn't completely reattach the flow in this case, but you do get some slight lift increase and then significant amount of drag increase, right? In this case, it doesn't really increase lift, but you got drag reduction here. So, okay, I just told you I don't want to do it, but we did it anyways, thanks to DoD giving us computer time. But we don't want to do this too many times, right? So we want to go to something that's a little cheaper and more manageable, and that's why we wanted to use the resolvent analysis. So let's look at the resolvent analysis results. I'm just showing, this is the 2D. This is actually not something I should be showing. Maybe I should be showing the 3D modes, but just for illustrations, this is what we'll get. We'll get a pair of forcing mode and the response mode. And of course, we have the amplitude as well. We'll have that for a range of frequencies and also a range of span-wise wave numbers, right? Now you look at this and says, okay, Sam, this looks fantastic because we have this particular gain distribution. Maybe we should just actuate right here, right? Doesn't seem like a bad idea. However, as we all know, this is a linear concept, right? So if we want to go from this type of flow, put some control in and then get this type of flow, it doesn't really make sense because, again, as we have all been discussing, you put in some perturbation, you want to influence the mean flow, so you need nonlinear interaction, right? And then hopefully it'll go to the right direction, right? Now, how should we go about that? So this might look very intuitive in hindsight, but let me just explain what we want to do, right? So you have lift and you have time, and then we're talking about linear response, right? Harmonic input, harmonic output. But what we really want is a nonlinear departure from that behavior so that you change the mean. So the way we assess that, right, is to evaluate the Reynolds stress from these primary modes that we'll see, the response side. You can compute those modes and then see if we can evaluate that, right? And then why do we evaluate the resolvent stress is because from physics or from our insights in flow control, we do know that we want mixing of the high stream momentum that's going over the wing and the slow flow that's over the airfoil after separation. So we want to improve that condition. So we want some mixing to happen. Now, what we did here is that we assessed this Reynolds stress over the wing, right? We have a window here. And then said, okay, can we integrate that and see what that metric would be, right? So we have the 2D version, the case where the span-wise wave number is 10 pi, 20 pi, 40 pi. Now 2D doesn't really work because you're not going to get that three-dimensional mixing, so you can throw that out, although it's the highest. So then you can look at 10 pi and 20 pi being useful candidates and maybe these frequencies, right? So this gives us some idea about where to go. Now, how should we do? And by the way, you can actually go through this in more elegant manner if you go through the nonlinear extensions of these resolvent analysis that we have been seeing, right? But we just want a metric at the moment. Now, how well would that do? So although I said we want to avoid it, we went ahead and did all the parametric studies to validate our claim, right? So each of these data points on these plots, this is drag, lift, and over D over the frequencies, and we're compiling all these cases from different span-wise wave number conditions, right? And what we're seeing here in color is that metric M in log scale, and the red ones are hopefully the ones that are kind of useful, right? And they do align with the regions where you have low drag, high lift, and pretty good L by D ratio, right? They're not perfect, but at least they narrow down the regions, right? So instead of having to do the full set of LES study, which costed us about 35 million hours, this can be done in matters of days. Okay, so for us, this was great. Now, do they actually work? And they do, right? We're not going to say they can pinpoint the optimal case, but they can narrow down the amount of cases to maybe a handful that we should be looking at. And if we do look at exact amount of CD reduction or lift increase, they're on the order of about 50% and 50% for lift and then minus 40% for drag. So we were really happy about this, right? So now we know where, at what frequency to actuate and also at what weight number to place these actuators in the streamrise direction. So let's go a little further. Okay, so now I'm going to say, okay, that was the vanilla version of our resolvent analysis. I want to go a little further with it. Now, first thing we're going to consider here today is what happens if we promote sparsity. Okay, the analysis that we've done was based on the L2 norm version of resolvent analysis. And when you look at the forcing mode, this is for a particular case, it's actually spread out over some region, right? Now, if I take this and go to my colleagues and experiments, they would say, Sam, that's great, but I can't force in the middle of the flow, nor can I force over a blob of region, right? So what you can do is to look into things such as the L1 norm, which promotes sparsity, right? So here's a little cartoon that I stole from my colleague's textbook, right? So if you look at the L2-based optimization for a 2D problem, usually the solution is like an intersect of two things, in this case, a circle and a line. That means your solution is A1 star, A2 star, say, they're non-zero. But if you change your norm, which is like an L1 norm, which is a diamond, one of them is zero, one of the other ones is non-zero, right? So you fill up a lot of your columns or your entries with zeros, which means it's sparse. Now, if you do this for our case, let's say the same problem. Here is a particular forcing mode, right, which has non-compact support over space. If you use a L1 based version, it shrinks it down to a point. Now, that's not guaranteed, but that's what we get, right? Now, you could still say, Sam, well, that's great, but it's still out here. It's not on the surface because I can't put an actuator out in the middle of nowhere, right? That's not a problem because I actually project all this onto the surface of the airfoil. And if you do, here's a coordinate along the chord. You can now actually see that if you do the regular version, you get these curves, the dashed lines, for each of the variables, rho u prime, rho v prime, rho w prime, rho e prime. But if you use the sparse version of the resolvent, it actually gives you these star values. So now I'm going to go back to the point of what kind of actuator should I use and where. I can now pinpoint to say this location, the 2% location, the chord is exactly where we should be placing our actuator. And furthermore, our thermoacoustic actuator that I was kind of saying all these nice things at the beginning may not be the best thing to do because resolvent analysis is saying that I should be using rho u prime and rho v prime as my actuation input, so momentum injection, right? Moreover, because I have rho u prime and rho v prime, the actual value of it, the amplitude, it's now going to tell me which direction I should be blowing at. So these techniques are now telling us a lot about how we should be doing flow control. Right, I'm going to talk a little bit about this because I really like this work by our colleagues in applied math, right? So this randomized numerical linear algebra is something that we've been getting into, and actually Ati and Beverly have been looking into this as well. It's a really neat concept when you have these huge operators. If you think about it, we get this massive matrix and all we get is a single vector sometimes, or maybe a few. So from a point of view of how much information you're extracting, it kind of seems a little wasteful. There's this concept called sketching, where you can pass a short and skinny matrix. This could be just a random matrix. You pass it through A and you get Y. This is called a sketch. And this sketch contains so much useful information, such as making like a basis to project your A matrix. And if you do so, you can actually, instead of doing all this large SVD, you can do a much smaller version of SVD and save up on computation and memory. Now, there are a few things you would have to do that's still costly for resolvent analysis. And I know Aaron's looking into that with time stepping methods, right? Well, when you combine that, you can actually do some wonders. This is the full resolvent analysis on the left-hand side that I showed earlier. This is the alternative one with the randomized resolvent analysis with the short skinny matrix, right? That used the sketching here with k equals 5. So width is 5. Actually, if you do this even better or in the right way with physics incorporated, you can turn this into k equals 2. In some extreme cases, you can do it with a single sketch of k equals 1. All right. Now, why does that help us? Because we can now handle bigger things like grids for higher Reynolds number flows. So we've been working with our colleagues at the Air Force Research Lab where they have the same type of flow, but at Reynolds number of 500,000, where the flow would look something like this, right? So here, we can now analyze where you're going to get the response modes and forcing modes, and they do exist indeed, right? And we can get their dependence on the frequency. And overlap means something in flow control. I won't go into it today, but this was really exciting. Furthermore, we can also look at the resolvent analysis of three-dimensional situations, three-dimensional flows. Okay, what else do I have? Okay, a few other things I want to say. When you do resolvent analysis, sometimes you have to be a little careful to find things that are subtle. So I'm going to talk about a Martian aerodynamics application of resolvent analysis. So this is slightly different. Mach number is higher. Mach number is at 0.85, where you could possibly get buffeting if the Reynolds number is higher. This Reynolds number is extremely small, 2,000. Now, if you do a standard Reynolds number or a resolvent analysis of this flow, what you're going to find is that you're going to get forcing modes here and a response mode like that, and a frequency that peaks up somewhere over here. This corresponds to the wake frequency. However, if you window it at the right way, so if you window it right here and it says, when can the shock oscillate? It turns out you can actually get the responsible modes to induce buffeting. Buffeting won't induce at these conditions usually, but if you perturb it the wrong way, it can. That's what this study is showing. So we're pretty excited to see this. And in fact, what we did was we put in this exact perturbation into the flow and started to see buffeting. Okay, so this was kind of a warning to us that although we don't see it at this particular condition, if the structure starts to vibrate at the wrong place, we might be able to see buffeting, which would be kind of bad for those little flying objects. Okay, last thing, this is kind of a plug to our upcoming meeting in Madrid. What happens if you have time-varying base flows? I work also in the area of network science. And one of the things that we do look at is how do things interact? So you have a lot of elements. How do these elements interact, or how are they interconnected? That could be really nicely described by network science graphs. And here, what you would get is what we call an adjacency matrix. And this adjacency matrix tells you how information can flow over this network. Okay. And I'll say this for next time, but you can describe how information can flow over this network by saying if the information is F, the influence, what you get is a response is Q. This looks awfully like the resolvent, right? A is not imaginary, it's actually a real parameter, but this looks very similar, doesn't it? Now, what's interesting is that in the network science community, they even consider the graph to be changing in time, right? A time varying graph. So you can actually incorporate that and do the analysis, and I'll save this for next time in Madrid. We're going to meet each other in about 1 month, I imagine. May, right? Right? So here, what I'm going to show is that you can actually construct a time-varying graph for two-dimensional isotropic turbulence and identify what is the right place to push or poke so that you can spread the perturbation or disturbance over the entire flow field. This is what Xian has done. And you can decompose the flow field or this matrix using SVD. And here is a movie of what happens if you poke this green region, which is identified to be the most sensitive region, and you can change the flow really, really fast. And we've shown this in our paper that how fast you can do it, and actually you can also reduce the fluctuation as well. So please stay tuned. So this is my summary. Do I still have time? I don't know. Doing okay? 1 minute? You didn't even look at your clock. It's like 1 minute. All right, so I think we have a really powerful tool that we're starting to leverage for flow control applications. We're really excited about this. Let's see. There's been a lot of extensions, not just by our group, of course, the entire community. I'll talk more about the broadcast analysis. That's the last part of the talk that I just spoke about. And, this is not just an academic exercise. We're really proud to say, like, we're now starting to apply this to flows such as like flow over an actual vehicle. This is a CRV, right? And we have some work that's been undertaken by our colleagues. So hopefully I'll be able to talk about that one day. All right, with that, thank you very much, and I'll be happy to take your questions.
Thanks, Sam. Great talk. I have lots of questions, but I'll try to just maybe roll 2 of them in here at once. So when you're doing this sort of sparsity promoting resolvent analysis, 1, can you comment on the cost of that versus a normal resolvent analysis? And 2, do you think that you would have gotten the same thing if you just would have spatially windowed and sort of done a parametric study of that?
So the cost is significantly more expensive because what you do is you're not doing an SVD anymore. You're actually doing an optimization problem. But I think that's a cost at least we're willing to pay, right? And it's doable, manageable. So I think it's okay. Now, the second question I didn't get. So you said the windowing. What do you mean by changing the window?
If you want to spatially localize the input, you can do that using the C and the B matrices, right? So would you get the same thing if you localize like that?
So that's actually a good question. You could artificially force to say, like, I want my input only in this region or on this surface, but that doesn't narrow down to a single point yet, right?
You could choose it.
You could, but that doesn't mean you're solving some optimization problem to give it a little bit of freedom. You're actually then narrowing it down to that point and seeing only the response. So you're not solving for the location at that point. You could, yeah. But that would be more of that's a parametric study that you'll have to do, right?
Sam, very, very interesting talk. Lots of material in there. I wondered if I could go back to you had a randomized slide or 2. And so I don't know any of this stuff. I mean, can you give us a little bit more? You're taking a random vector, you're hitting it with A.
Yes.
How does that work? What are you doing here?
You hit this A matrix, or you hit this sparse. Well, it doesn't need to be sparse. It's a test vector. Or test matrix, which is randomly generated just like this.
Yeah.
You hit it with A.
Yeah.
The action of A is held in this matrix Y, which is called a sketch.
Yeah.
So it's stretching psi in certain directions, right?
I see.
And you can use that information, for example, to construct a basis, right, or bases to project A onto.
It's like dual to the Krylov space, and it seems like
it's very there's some similarities.
So rather than keep on multiplying by A, you take randomized vectors.
Yep, exactly. You do it in one shot.
I see.
But then you're I'm sorry.
No,
You're counting on big separation of eigenvalues or singular values.
You're absolutely right.
Okay.
You're absolutely right.
So it's just like as if you said A was low rank or something, or almost. Anyway.
Yeah.
Just big separation.
So if you don't
projecting onto the largest one.
You're projected onto the largest response, and if you don't have a big separation, then you'll have to consider more, a wider test matrix, right? That's the challenge with us, is that how much, if you don't know it ahead of time, you kind of have to check, right? Go back and check whether there's a sufficient separation.
Okay. I think we have a question from Zoom.
From Bernd, probably. But here's one thing that I want to mention. If you have shear flows and you have enough separation that you know ahead of time from physics, it seems to work pretty well. Yeah. Bernd,
go ahead.
I can't hear him.
But he wrote that.
He wrote, yeah, I see that. Can the resolvent analysis anticipate gurney flaps or high frequency forcing, something which may not be in the data? Bernd, when you say that, do you mean like to design it, or can you elaborate on this question a little bit? Unfortunately, so hold on, can I hear him? I can't hear him. Wish I could.
Okay, I try now another channel.
Oh, no, I can hear you now.
Okay, wonderful. So I wonder, so this is an inspiring approach. I wonder how far you can go with this resolvent analysis, and give you a couple of ideas. If you have the airfoil and you have a gurney flap, then you can also do a very nice lift increase separation control, but the gurney flap is essentially cannot be in your original data. Another thing is maybe you have to do high frequency forcing, something like a turbulator, change the structure of your boundary layer in order to achieve your separation delay. Maybe it is good to play with multiple frequencies at two different locations. So I would like to get a feeling of you, how far you can stretch the method of the resolvent analysis to get these, say, steady changes of the flow, or where you need to invent new structures in the flow to achieve your control goal.
Bernd, I haven't thought that far ahead, but since we're married to the base flow that we provide, gurney flap may be a little tough because you're going to have to introduce a new shape. Now, as far as the multiple frequency goes, I think we can do something about that a little easier. But even gurney flaps, if you want to consider maybe the zero frequency mode, I think there might be some room for developing something like that. Yeah.
And could you connect it some? So it looks like the approach is linked to open loop forcing. How could you predict a good closed loop flow forcing?
There was a talk on that by Aaron, so maybe we can talk about that more. But there seems to be a nice way to close the loop as well.
Okay.
Yeah, and Mike, question?
Okay.
So this is very naive, but this popped into mind from the last question. So can you do something like a flow K-theory version of resolvent analysis where you linearize around a time periodic state rather than a steady state?
We are working on it, sir.
Very good.
Yeah, so we're looking into, well, not exactly on the amplitude side, we're trying to work on that part, but we have a phase reduction analysis type approach that we're working on. So now we're looking at the timing, right, where we are with respect to how the base flow or the limit cycle changes. So please stay tuned. I'd love to get your feedback on that as well. Clancy's work? Yeah, I think I cited his work, right? Oh, this one. Oh, I'm not aware of this particular work that Clancy's doing there. Which one? Oh, harmonic. No, I think I cited it somewhere. Yeah. Sorry about that. Yeah.
Okay, I think with that, we are now allowed to have lunch. So thanks.
Thank you.
Back at 1:30.